So today we're going to be talking about a really beautiful equation and how it's being proven. So we know e to the I pi's power plus 1 is equal to 0. So this is a beautiful equation made by Euler, which is a really famous mathematician in the past. This is called beautiful because you are relating 5 different numbers into one single equation. So we know that 1 and 0 are really key numbers in the number system, and we also have I as imaginary number, and we have pi and e, which are two irrational numbers that are pretty significant in math. So, but why is that the case? Why do you have an irrational number raised by an imaginary number be equal to -1? So this is something that we have to consider. If you can check out the second video that I made, it was about number system and Euler's identity. So today, instead of applying it, we're going to discuss the proof of this such beautiful equation. So to prove this, let's talk something about Taylor's series. So Taylor series. So, well, why is Taylor series something that we have to consider in order to prove this? Taylor series states that e to the x is equal to 1 plus x squared over 2 factorial, and then plus x cubed over 3 factorial, and then plus x to the 4th over 4 factorial, and then plus dot dot dot. So this seems pretty interesting, and if you try to expand this, then you initially get it's closer and closer to e to the x as x approaches to infinity. But why is that so? But why is this the case that will lead to e to the x power? So we can see that a really important property of e to the x is that the derivative of e to the x is always e to the x. Well, why is that? Well, this we can prove by induction, because we know that dn minus 1 over dxn minus 1 is equal to e to the x, and the derivative is always e to the x. So this basically states that whenever, despite the number of time you take the power of e to the x derivative, then you always get the same answer of e to the x. So this kind of motivates us to generalize a function for e to the x. Well, we can let e to the x equal to a1x plus a2x squared plus a base 3x cubed, and then plus dot 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 plus a base n xn. Well, check this out. Now if you a0. So now if we take the derivative of this function when e is equal to 0, right? So if we take the derivative of this function, then this is essentially equal to a1 plus 2a2x. So look at this, we're just applying the power rule over here. So now we actually have, now we have n a n x to the n minus 1's power when n is going to infinity. So this is actually pretty significant, because now we see that a0 is essentially equal to what? Equal to a1, right? a0 is equal to a1, and a1 is equal to 2a2, because looking at here, we're only matching the same coefficients. So we're matching these, we're matching these, we're matching these, we're matching a base 3 x cubed, we're matching with 4 times a base 4 x cubed. So we also have a base 2 is equal to 3 a base 3, and a3 is equal to 4 a base 4. So now this can be proven by induction that an is equal to a0 over n factorial, because we know that an is equal to a base n minus 1 over n. So if you just put it backwards, then you're going to get this result at the end. So now we know that the first term must be 1, right? Because you see that if you are plugging x as 0, then a0 will be the only constant, so a0 is equal to 1. So basically, we can see that these are connected up because an is basically equal to 1 over n factorial. So now so now we're just going to plug it back in. So we can see that e to the x power is equal to 1 plus x over 1 factorial, which is essentially x, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus plus x to the nth power of n factorial as n approaches to infinity. Well, you can see that this is actually a really powerful insertion, and this will be used to prove the identity